Change is the only constant in the universe, but how do we actually measure it? If you are driving a car, your speedometer tells you how fast you are going at this exact second, not over the last hour, but right now. In mathematics, that right now moment is what we call a derivative. At its simplest level, a derivative is the measure of how a function changes as its input changes. If you have ever looked at a graph and wondered about the steepness of a curve at a single, solitary point, you're looking for a derivative. Think back to basic algebra. We'll remember the slope formula, rise over run, but that requires 2 points. What happens when those 2 points get closer and closer until they are almost the same point? This is where the magic of the limit comes in. The derivative is defined formally as f prime of x equals the limit of f of x plus h minus f of x over h as h approaches 0. By shrinking the distance between 2 points to essentially 0, we transition from an average rate of change to an instantaneous one. It's the difference between saying I drove 60 miles in 1 hour and saying at this price heartbeat, I'm moving at 60 miles per hour. But why does this matter beyond a classroom whiteboard? How do we actually use them? Derivatives are the primary tools for optimization. If you're a business owner, use derivatives to find the exact point where your profit is maximized or your costs are minimized. If you're an engineer, you use them to calculate how much stress a bridge can take before it hits a breaking point. In physics, the derivative is the bridge between dimensions. The derivative of your position is your velocity. The derivative of your velocity is your acceleration. We use these calculations to land rovers on Mars and to keep satellites in orbit. How are derivatives applied in our daily lives? They're hidden in plain sight. They power the algorithms that predict the stock market. They help meteorologists model the path of a hurricane. And they allow AI to learn by adjusting weights in a neural network to reduce error. Every time something moves, grows or fluctuates, a derivative is there to describe it. In this video, we are going to strip away the intimidating notation and look at the heart of calculus, the art of measuring the instant. Let's dive in. Rates of change. For any function f of x, change in x is calculated by x2 minus x1, and that of change in y is just the difference between functional values evaluated at the 2 points. Let's look at this half parabola. Let's again draw a line through 2 different points, 0, 8. Let's again add 2 more lines so that we can create a right triangle. The adjacent side is the change in x, and the opposite side is the change in y. The slope of second line to the graph of the parabola is given by the ratio of the change in y to change in x, which means slope equals f of x2 minus f of x1 over x2 minus x1. What happens if we have to shrink our right triangle all over the way? Until 2 endpoints of the hypotenuse of the right triangle get near and near until they coincide, just like this. Well, the magic happens here. The slope of the second line approaches the slope of the tangent line drawn at the point. This is what takes us to the world of the term derivative. Therefore, just in a simple term, derivative is actually an instantaneous rate of change. Let's move this bunch of stuff to the left and see how we can actually calculate its derivative. Let's also remove these lines. We don't need them this time. The graph to the left actually represents our function at the top, which is f of x equals 0.5x to the 2 plus 1. By applying the difference quotient and evaluating the limit as the variable h equals 0, gives us the derivative of our function. Therefore, the derivative of our function is x. There, of course, seems like there is actually something else which governs how derivatives actually operate other than the slope of tangent lines.